Hello, and welcome to this section on equilibrium. This is just a short demonstration on this section about how to calculate different equilibrium concentrations using the equilibrium expression, and also a little bit about something called solubility equilibria. So I'm going to go through a few examples for you, and let's get started. Okay, so what if we want to calculate equilibrium concentrations, different concentrations when the system is at equilibrium, using that equilibrium expression? Here is a sample problem of that idea. We have gaseous phosphorus pentachloride decomposing to chlorine gas and gaseous phosphorus trichloride. Now, first thing to tell you, the very first thing we need to do is write a balanced chemical equation. So let's go ahead and do that. Phosphorus pentachloride in the gas phase and is going to decompose into phosphorus trichloride. It's a gas plus chlorine gas. Okay, now the next thing, let's keep reading. In a certain experiment at a temperature where K equals 8.96 times 10 to the negative 2, now I have a typo there, the equilibrium concentrations, there shouldn't be an M in there, of the phosphorus pentachloride and phosphorus trichloride were found to be 6.7 times 10 to the negative 3 and 0.300 molar respectively. So we're given the concentrations of this and this. And we are asked to calculate the concentration of chlorine present in the equilibrium. So what we want to know is concentration of chlorine. Well, we know how to write an equilibrium expression. Let's go ahead and write that down. K equals the concentration of chlorine gas. Concentration of phosphorus pentachloride over the concentration of phosphorus pentachloride. So now that we have that, and again, our equation is balanced. We have one phosphorus on the left, one phosphorus on the right, 5 chlorines on the left, and 5 chlorines on the right. So that we don't have any coefficients for this. We know the values for phosphorus pentachloride and phosphorus trichloride. We are also given the value for the equilibrium constant. So we can go ahead and just plug those in. We have the equilibrium constant 8.96 times 10 to the negative 2. And that is equal to the concentration of chlorine gas that we want to find out. We know the concentration of phosphorus trichloride is 0.00 molar. The concentration of phosphorus pentachloride is 6.7 times 10 to the negative 3 molar. From here, you can isolate this variable on the right side of the equation by dividing both sides of the equation by 0.300 and dividing both sides of the equation by multiplying both sides of the equation, by 6.7 times 10 to the negative 3. When we do that, we get the concentration of the chlorine gas at equilibrium to be 2.00 times 10 to the negative 3 molar. Now we're going to look at something called solubility equilibria. When we dissolve solids in water, equilibrium is often established in these circumstances as well, but we just call the equilibrium expression, in this case, KSP, and you've seen this before, the solubility product constant. And that's what this is. We talked about this before when we were talking about water. Water always has the same solubility product constant at a given temperature. Well, so do other systems. We're going to look at a system like that. Here's a calcium fluoride. We put solid calcium fluoride in a beaker, put some water in there, and it's going to dissolve And as the calcium fluoride dissolves into its respective ions, we also have the reverse reaction happening, where we have the fluorine and the calcium ions combining to reform calcium fluoride solid as well as a precipitate. So we have this in equilibrium going on at the same time. How do we write the equilibrium expression for this? It's going to be just the same, but we're going to call it the solubility product constant instead of, it is an equilibrium constant. So when we write that, it's going to look like the equilibrium constant, or the solubility product constant, is equal to the concentration of the calcium ions times the concentration of the fluoride ions squared, right? We have this coefficient, and that's it. These are both aqueous, they're in solution. This is a solid, so its solubility, or its concentration remains constant. It cannot change or fluctuate. So this would be our solubility product constant value right here. This is the equilibrium expression for this system. Now, we're going to try a problem calculating the solubility product constant. And this will look very similar to what we've already done. We're just applying it to a situation where we are dissolving solids in water. So let's read the problem. We have copper 1 bromide right here. It has a measured solubility of this much at 25 degrees C. That is, when excess copper 1 bromide is placed in 1 liter of water, we can determine that 2 times 10 to the negative 4th moles of the solid dissolves to produce a saturated solution. Calculate that solid's solubility product constant value. So what are we going to do? First we have to write a balanced chemical equation. So let's start right there. We have copper 1 bromide solid that is dissolving into our copper ions, aqueous, plus our bromide ions, aqueous. So there we have it. We also know KSP for this system, the solubility product constant, is going to be equal to the concentration of copper times the concentration of the bromide ions. It's a balanced equation, right? We have one copper on each side, one bromine on each side. Therefore, KSP, we're not squaring anything. We have all one-to-one coefficients, and that's where we can start. Now, we are not given in the problem the concentrations of the copper and the bromide ions, are we? We are only given up here concentration of the copper bromide. It has a measured solubility of 2.0 times 10 to the negative 4th moles per liter. We know, and if we have our little beaker and we are dissolving the copper bromide in our beaker here, we know that we are going to get some copper ions and some bromide ions. 1 mole of copper bromide is going to produce 1 mole of copper ions. It will also produce 1 mole of bromide ions. So we know that the concentration for the copper bromide per liter will be the same as the concentration for the copper ions and for the bromide ions. So we can go ahead and finish our calculations here. We can say our KSP, if we substitute this in for the values, 2.0 times 10 to the negative 4th moles per liter. And we'll multiply that also by the same for the bromide ions, 2.0 times 10 to the negative 4th moles per liter. And when we multiply that out, that gives us 4.0 times 10 to the negative 8. And just like our other equilibrium constant, the solubility product constant is unitless. We just omit the units for it. So there's our answer. Hope you enjoy doing some of the practice problems. There's a worksheet that you can practice some of these on, and let me know if you have questions. Look forward to seeing you in class. Bye.